Today we will discuss mass spectroscopy. Mass spectroscopy is an analytical technique, and it is used to measure molecular mass of any substance. Actually, what it measures is we will learn in a couple of slides later. It does not actually measure the mass per se. It measures mass over charge ratio. So we call this uh, M to Z. So the charge is always a plus one. So therefore, M over Z is always equals to M because Z is the charge and charge is plus one. So it doesn't change the number. So indirectly, we can measure mass because charge value is always plus one. The theory behind this mass spectroscopy is quite old. Uh, it was first used by J.J. Thomson, who discovered electron, by the way, in early 1900s. And using this technique, J.J. Thomson was able to discover that elements have more than one isotope because he was able to find that their same element has two different mass values. So from that, it was discovered that different isotopes are present. But back then in early 1900s, I'm talking about like 1910s. Um, this technique was not well developed. It wasn't accurate, and there were lots of flaws. And as the time progressed, this technique got better. And it wasn't until 1950s when uh, this whole mass spectroscopy was adopted by mainstream chemistry, measurements. So earliest commercially available mass spectroscopy instruments um, were commercialized or used in 1950s. Even then, it wasn't that accurate. And we'll go over it why they were not accurate and what new advances have been made in few slides later. But that's when it got really popular. So modern mass spectrometers are quite accurate, and there are mass spectrometer available who can distinguish the molecular mass up to fourth decimal place. Okay, so they are so accurate. And not only we can obtain the information about the mass of any substance, we can also from modern instrument we can also obtain information about the structure of the chemical. Chemists rarely use mass spectrometer to analyze the structure. It's not that convenient per se. So main purpose is to measure the mass, but we do get quite useful information about what the composition of molecule is. Okay, a new application of mass spectrometer is the is in recent times is determination of many complex protein structures. Uh, that part is beyond the scope of this book, so we're not gonna discuss how the structure is analyzed, how the protein structure is analyzed. So, but that's a new recent discovery. So as I discussed earlier, mass spectroscopy is a technique which measures mass to charge ratio of ions. But the charge is always plus one, so therefore mass to charge ratio is technically equals to mass. So that's how we calculate the mass. Okay.
Stop.
Okay, so not only it gives the value of mass, but it can also be used to determine this sequencing of proteins. This schematic diagram shows how the mass spectrometer works. So in a modern mass spectrometer, uh, what so this is the inlet. Okay. So spectrometer has three main components. So in first component or first part, the sample is converted into gas or vapors. So that happens here, and those vapors are then, so the neutral atoms are then stripped off by one electron. So one electron is removed from the neutral atom. So and that happens in this chamber. Okay. So in this chamber, the atoms, the vapors. So first first the sample goes in, forms vapors here, and there is an inlet here. From this inlet goes to this chamber. In this chamber, it is bombarded by something. That something is fast moving electrons, or in some other cases, is fast moving atoms. So there's a bombardment happening to our sample. So this bombardment will remove one of the electron from the atom. So when electron is removed, our atom becomes a positive ion. Okay, so that positive ion, uh, there is an electron plate. So negative charge is on this side, positive is this side, because our atom is now positive charge. So it gets pulled towards this plate, and there is an opening here, and it passes through it. And when it reaches at this stage, there is a magnet, and that magnet bends it and bends and then sends it to this side, and there is a detector, and then the sample is detected here. Now, depending on what is the size of the ion, when the sample is bent here, if the size is large, it will not deviate from its course. It will stay on its course straight if the size is large or heavy ions. If the size is small, it will start deviating. The smallest size or the lightest one will deviate a lot. So the lightest ions are detected somewhere down here, the heaviest one up here. So depending on where the sample was detected, computer will analyze, and from that it will calculate what the structure, what the molecular mass is. Okay, so that's a really simplistic way of explaining how a mass spectrometer works. Okay. So, any question so far? Okay, so let me go over one more time.
Wait, I have a question.
Yes.
If these ions, if these like compounds are in the gas phase, how are they able to be an ion? That's what I thought. Ions were only allowed to be like in the aqueous phase, or maybe I just had a misunderstanding.
No,
In
those are
the,
the dissolved ions. So these ions are unstable ions, and they are produced
Mhm.
as such. For example, if I have a helium atom, right?
Mhm.
Let's say I injected helium atom in here,
So this
right?
takes a lot of energy.
It takes a lot of energy. Yes, yes, you're correct. So helium atom means it has two protons and two neutrons in the nucleus, and two electrons around it, right?
Mhm.
So what happens is when this helium enters this is called ionization chamber. In ionization chamber, you see these dotted lines there.
Yeah.
So those dotted line represents fast moving electrons, or in some other cases, it could be fast moving atoms, some gas atoms, really, really fast moving. Okay. And when those fast moving electrons, those act like a bullet. So those fast moving hit here, or eventually they will hit. So they will knock this electron out of it.
Mhm.
Okay. When this electron is knocked out of it, helium becomes, which was neutral by the way, helium becomes helium positive. Okay, so we that's how we represent. It's not stable, and it doesn't have to be stable. It just need to be stable enough to reach at this plate. After that, it dies. It dies. Okay. Yes, it's not stable, whatever it makes, and it may decay further also, and something else may happen. So that's what happens. So ionization chamber knocks one electron out of the molecule, and molecule becomes a, so we call this a radical cation because it will have a one. Well, helium is not the correct example to use because mostly we use this for organic compounds which has carbon and hydrogen atoms, and we will discuss in a couple of slides later what kind of electrons are knocked out and how it happens. But for now, just remember that fast moving electrons will knock one electron out. And yes, you're correct, it takes a lot of energy. And you will learn uh, later in this chapter that the energy required to break a sigma bond is is about like 1,000 to 1,500 kilojoules. Oops, sorry, it's about 1,000 to 1,500 kilojoules per mole. And these fast moving electrons, they have almost 5 to 10 times more energy than required to break a bond. So yes, so they have a lot of energy, so they can break any bond. Okay. So once atoms are stripped of one electron, they become radical cation, like shown here. So because of the positive charge of radical cation, those cations are attracted towards this plate because this plate is negative charge, and there is a slit here, and they pass right through the slit, and they come in contact with magnetic field. Magnetic field will uh, bend them and push them. If the size is large or mass is heavy, they will not be pushed that much. They will retain their course and they will continue to move and they will get detected here. So heavy atoms are detected on top of the detector, as if the lighter ions are come under the magnetic field, they will be pushed more. So smaller the mass, more will be the bend, and the lightest one will be detected at the bottom of the detector. Then the computer calculates from the position where the sample was detected. So computer calculates the mass because the computer knows that this much AMU will be detected here, this much AMU will be detected here. So computer has that data. So from that data, it can calculate what is the AMU value of that sample wherever it was detected, right? Any
Mhm.
question? One more thing I would like to mention, like I said, helium is not a good example. Let's take a relevant example. Let's say instead of helium, we have a, let's say, butane, right? Butane gas. So yes, in initially, when butane gas is bombarded with the electron, butane gas will lose one electron and will become a butane cation. Not stable, right? It's not stable, yes, but it will lose one electron, it will become. Before this butane cation reaches the detector, before it reaches all the way down here, this butane cation may further undergo some other breakup. It may break up into two ethyl cations or one ethyl, one propyl. Something else can also happen, right? So this we call fragmentation. So in mass spectroscopy, what happens is when uh, the molecule is bombarded with these fast moving electrons, not only they will produce the radical cation, the radical cation can further break down into smaller fragments also. So all these fragments will reach, and depending on the mass of the fragments, we will get multiple signals. And those fragments do help us to predict what the structure of that molecule would be. Now, imagine you have 100 molecule injected. Out of 100, maybe some, first of all 100 will give you molecular ion, but then out of those, some fraction will give breakdown further. So there will be a percentage range how much molecular ion reaches here and how much fragments reach here. So all of them will have different percentages fragments. Some fragments will have larger percentage, some will have smaller. So we'll get a bunch of lines, and I'll show you a spectrum. Well, that's what spectrum looks like. All of these lines represent a fragment of the molecule which is reaching at the detector. Okay. Any questions so far? So this diagram which I just discussed now, this one, okay. So this particular kind of mass spectroscopy or mass spectrometer is known as electron ionization mass spectrometer, or EIMS, because we are using electrons to ionize our sample. That's why it's called electron ionization mass spectrum. This kind of technique is what we call a crude technique. Crude technique is that technique in which the ionization is not selective. Ionization is we are just bombarding with a fast electron, and it doesn't distinguish. It's gonna break down into bunch of smaller fragments. So it's not gonna give you just one fragment and one molecular mass. It's gonna give you a bunch of fragments, bunch of peaks, and then it's up to you to analyze the system. So this is one of the oldest technique, still useful, um, but it destroys our sample. It breaks down completely. Okay. There are other kind of techniques also available. Those are called uh, fast atom bombardment, MALDI, chemical ionization, and I'll briefly discuss about them in a little while later. I'm going to focus on electron ionization for now. One of the disadvantage of this technique is the electron ionization is that our sample has to be low molecular mass sample only. It is not useful for heavy atoms. Heavy means like polymers, like really heavy, whose mass is more than 10,000 AMUs or something like that, really complex. The small molecules like small alcohols, small ketones, aldehydes, they all work fine here. The other problem here is that sample must be a gas to begin with. If our sample is already a gas or a highly volatile liquid, this technique works well. Uh, because if it's a highly volatile and we have high temperature and there is a vacuum also. So this vacuum along with high temperature is good enough for most of the liquid samples and most of the gas sample. Or gases are already fine. But there's a problem with solid samples, especially those solids who do not evaporate and become gas. So the point is, if our sample is not gas, we cannot use this. It's So for solid samples, there are some additions we can make. So what we do is we put our solid sample on a tip. So this is solid sample. So we put it on a metal electron tip and we heat this up. And when we heat this metal tip, and our solid will melt and evaporate, and then we inject it in. So it is okay for some solids who we can evaporate. If solid is cannot be evaporated, then we cannot use this technique. Then there are some other kind of mass spectrometer available, but not we cannot use EIMS. Okay. So once the sample is in this ionization chamber, this chamber, they are bombarded with fast moving electrons. The energy of these fast moving electron is 70 eV. So eV stands for electron volt. Electron volt is another unit to calculate energy. We can convert into kilocalories or kilojoules if we want to, but instruments are mass spectrometers are defined in terms of eV. So that's what I know. So it's about 70 eV. And most of the bonds and other electrons can be uh, broken up by 10 to 15 eV energy. So about 10 to 15 is enough energy to break or dislodge any electron from any atom or molecule. So as you can see that our energy is much higher than what is needed to break. So that's why this is good enough. This is more than enough to break any bond or more than enough to dislodge any electron. Okay. So how the electrons are broken? So this is the fast moving electron. The energy of this electron is about 70 eV. When this electron hits any molecule, for example, our molecule is methane gas. When it hits any, uh, now methane gas has many electrons. So there are sigma bonded electrons, well, sigma bonded electrons. It doesn't have any pi or any non-bonding. So one of this electron, which one will be broken up? Not important for now. One of this electron will be knocked out and the molecule becomes a radical cation. Radical cation means that it has a free radical or one unpaired electron and a positive charge. See, one electron hit, two came out because it brought one electron out of the molecule. So this is a molecular ion or radical cation. The mass of radical cation will be same as the parent molecule. So when we measure the m over z of this species, its mass will be same as the parent molecule. Okay. Now, as you can see that in methane molecule, there are 8 bonding electrons, right? And one of the electron is knocked out. Now this one has 7 bonding electrons remaining. That's why there is a positive charge because it has one less electron. And why there is a radical? Because if there are 7 electrons, 6 of them will be paired up, one of them will be unpaired. That's why we show it with a radical symbol here. So this kind of system is known as a radical cation, which means it does have a positive charge as well as a free radical. Is there any question I can answer so far about this technique? Okay. Shall we continue?
Is that is that going to be a fish hook arrow, or is
Is
that?
Say that again, please.
The arrow that you use for the electron to break that first bond, is that a regular arrow or a fishhook arrow?
Oh, it's a regular arrow. Which one? This one?
Yeah.
There is no arrow. We don't know where this electron is going. It's not a mechanism.
Oh, okay.
Okay, so we don't know which electron is fast moving. That 70 eV electron is breaking up. So we cannot we cannot use the fishhook arrow because we don't know the mechanism. So molecular ion is the radical uh, cation which is formed by removal of a single electron. Like I said, we don't know which electron is going to remove. There are 8 bonding electrons, and in some other molecules, there might be double bond or pi electrons, there might be lone pairs. So we don't know which electron is going to move, but for our purposes, it does not matter which electron is lost. Okay, it doesn't matter because uh, as long as we get a molecular ion and it gets detected by the detector, we're gonna get our signal. So uh, we don't know which one. We will get some idea later on that which electron will be preferably broken up, but at this point it doesn't matter. So instead of showing, so like Gabriela was saying, imagine if I know that electron is being removed from this bond. Imagine, I don't know, but just for the sake of argument, let's say that it's being removed from this one. Then I would show my radical cation to be like that, because I know that is it removed from this, right? But because I don't know which electron is being removed, I do not show it like that, right? So I just, because I don't know where it gets removed. So all I can do is I show the same molecule exactly, and I put a parenthesis, and there I put a positive charge. Outside the parenthesis means that somewhere within this molecule it got removed somewhere, and I don't know where it is. Does that make sense? That's why we use the entire structure within the brackets, and there we put the positive charge. Because if I would know that where it was removed, then I would show it there. Now, to answer another question, in some cases we do know which one is removed preferably. For example, the lone pairs are easy to be removed than the sigma bond. Similarly, pi bonding electrons can be easily removed as compared to sigma bonding electron. So when we do know that where the electron is getting removed, then you can show, for example, in case of this ether, okay, we know that non-bonding electron or lone pairs are preferably removed. You can either show the molecular ion like that. In this way, you can say, oh, I don't know where it got removed. But because I said that we know that non-bonding are preferably removed, you can also show it here because we are almost certain that none of the sigma bonding electron will be removed before one of these non-bonding are. So this is the preferred way. So what I'm saying here is that if we have ether, I'm going to write my own ether. And we bombard with an electron, fast moving electron, we know for sure that it's going to remove one of these non-bonding. So in that case, you can show the structure like that, because you know. Or if you still have any doubt, you can simply just show it like that. Both are correct. Both way of showing the molecular ion is correct.
Wait, Professor?
Yes.
So in the red writing that you just did, um, oxygen has both of its sets of lone pairs, and in the
Mhm.
green drawing right above it, it only has one set and then the radical. Um, so if you're going to draw it like the bottom one, do you put it as a neutral atom and then
In the brackets, yes. You are putting it
okay.
outside here, and that means that one of the electron, we don't know which one of the electron got removed.
Oh, okay. Okay.
Okay, so that's why we write the exact structure within the brackets. The top one is showing that which electron did got removed. Okay. Is there any other question? Is that okay so far? Like I mentioned earlier, that before the molecular ion reaches the detector, it can further break down, or electrons, fast moving electrons have enough energy, they can break down other sigma bonds also. So it means that the entire molecule not gonna stay as a complete molecule. It's gonna get fragmented. It's gonna break down into further smaller fragments. And all those fragments gonna reach at the end or at the detector. So we will get bunch of signals. Okay. So in mass spectrum, a plot of relative abundance of ions versus the mass to charge ratio is plotted. Whichever peak is the most abundant, whichever that doesn't have to be the heaviest one. One of the fragment will be the most common fragment. So that peak will be assigned an arbitrary value of 100. So we call this 100% peak. Just an arbitrarily, we call that 100. For example, let me just take the same example, this one. So when this breaks up, maybe bunch of them will break up into molecular ion, bunch of them. Imagine we start with 100 of these molecules. Out of 100, maybe 10 of them broken up into this one, maybe another 25 broken up into this one. Okay, so where they break from here, right? So another fragment, maybe they break from this side. So remaining, I don't know what is remaining, 70, 65 broke at this, right? Interesting thing is that when the fragments break, one side will get a positive charge. For example, this side, the other side will get a neutral lone pair. Similarly, one side get a positive charge, the other side get a neutral fragment. And detector only detects the positive charges. It does not detect the neutral fragments, right? So in this case, the largest fragment is this one. 65 of them are breaking up into that. So this peak will be the largest peak, and smallest peak will be this one. Most of the time, the molecular ion peak will be the smallest one. Okay, so let me take a look at, let's take a look at this sample. We'll discuss about the fragments later on, but okay, so this is a mass spectrum of dopamine. Okay, so dopamine largest, so its molecular weight is 153, and we do get a peak at 153. So this peak is molecular ion peak, but that's not the biggest peak. We are getting biggest peak at 124. So some fragment out of this molecule, so this, when this molecule was broken up, one of the fragment which reached the detector had a molecular weight of 124. Okay, and that fragment is the most common. So most of the molecules, because we don't inject one molecule, we inject bunch of molecules in our sample. So most of the molecule broken up into a fragment whose weight was 124. Okay, so what it was, we'll see in a little while later. Also, you see these tiny peaks here, bunch of the tiny peaks. Like there's one peak here, there's one peak here, right? So it means there is a probability that molecule is breaking into some obscure fragments, but not very common, very few. So what we do is we tell the instrument to give us peaks which are some percentage of base peak. Because if we get all the peaks which are coming out or detector is measuring, we'll get so many peaks that it's almost impossible to analyze anything. What I mean is that if, so in this case, it's showing all peaks which are greater than 0.5% of base peak. It means all the peaks which are at least 0.5% of the base peak, because we call this base peak 100. If this base peak is 100, so 0.5% means any peak which is bigger than 0.5%, only that will be shown. Any peak which is smaller than 0.5% will not be shown. Why it's done so? Let's look at this one. If we calculate the peak, same molecule, if we calculate all peaks above 5%, let's go back, above 5%, so 5% is here. So above 5%, we get only 1, 2, 3, 4, 5, 6, 7, and maybe this one 8. So we only get 8 peaks. If we measure all the peaks above 1%, we have 31 peaks. If we measure all the peaks above 0.5%, we have 45 peaks. And if we measure all the peaks above 0.05%, we have 120 peaks. Now, analysis of all these 31 or 45 or 120 is almost impossible. So these are not very interesting. We only look for the large peaks like this one, this one, this one, and the molecular ion. So in this entire spectrum, I'm going to focus only on these 4 peaks, or maybe this one, fifth. Interpretation of rest of the smaller peaks, not gonna give any useful information, so we don't waste our time, and many times we don't even ask instrument to measure those small peaks. We only measure the large ones. Okay. Okay. By the way, this dopamine, this molecule is a neurotransmitter. It is produced in our brain, and it's involved in coordination of muscle movement. And lack of production of dopamine, this one leads to one of the reasons for Parkinson disease. Those patients don't have control over the motor movement of muscles, and many times externally dopamine is administered to those patients. But some interesting, I find that interesting knowledge. Okay. So the technique which we have discussed so far is called EIMS, or electron ionization mass spectroscopy, because we use electrons to ionize the sample. Like I mentioned earlier, this is a crude technique. Electrons do not distinguish which break a bond to be broken up or which electron to be removed. They just get bombarded everywhere and they fragment the molecule and we get bunch of signals. There are other mass spectroscopy techniques available. One of them is fast atom bombardment. In this one, uh, we use fast moving helium atoms. So in electron ionization, we use electrons, and the energy of these electrons is 70 electrovolt. So about 5 to 8 times more energy required to remove any sigma bonded electron. In fast atom bombardment, it's similar to electron ionization, but instead of electrons, we use fast moving helium atoms. So fast moving helium atoms are used uh, to remove one of the electron. Now, helium atom is much larger than electron, so therefore the energy in this fast moving helium atom is also a lot higher. In fact, it is much more greater. It's almost like 1000 electron volt or even more than that. It's more than 1000 electron volt. So in moving or fast atom bombardment, anywhere that's we call this keV range, kilo electron volt range. Kilo means 1000. So you can see it's much more energetic as compared to EIMS. What do you think? Is it a refined technique? Is it selective, fast atom bombardment?
No.
It's not gonna be selective. It's gonna break down everything. It is used in bigger atoms, bigger molecules, because it's gonna break down the big molecules into smaller fragments easily, and then they can be analyzed. The another technique is which is also a crude method is chemical ionization. In chemical ionization, we use chemicals to remove electrons, and most of the time it's acid base. So if our sample is a Lewis base, we use some acid, um, right? Because acid base gives electron to the acid, right? So then base will become the positive charge. So in those cases, we can use the chemical ionization. That's also a crude technique. So all these three are not selective. On the other hand, there are two, yes.
In my physics class, we talk about like smashing uh atoms together, so you could like break down the protons. This type of energy that we're doing, or this type of
It's not going to break down the atom.
it's not gonna break down
No, no, no. See, it's enough to remove.
the
So
electron.
breaking down the atom means breaking down the nucleus,
Yeah, yeah. So
right?
this
So nuclear forces are extremely great, large. These techniques are enough to knock these electrons out.
Mhm.
So they're not going to break the nucleus. They're not going to break down the atom. You're going to need an accelerator
Mhm.
to break
So
the
as
nucleus.
far as like how fast the protons are moving, or not the protons, I'm sorry, that like the helium atoms or the electrons, like they're not like moving like towards.
They're not moving really fast. No, 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 not that fast. Remember, our instrument is tiny. So the one which you are talking about in that is like 22 miles of
Yeah.
accelerator. So they keep moving that, they keep accelerating that atom for a while. And here we accelerate these atoms for like fraction of a second, and it's like barely 5 inches.
Mhm.
In that space and at that time period, it's not going to accelerate a lot, but it's going to accelerate enough to break the electrons. Okay.
Mhm.
Now, the two selective techniques uh, we have is first one is matrix assisted laser desorption ionization, or also known as MALDI. In MALDI, we use laser to remove electrons. So lasers have enough energy and they are selective. So when we bombard the atoms with a laser, it's only gonna break one electron. So it's gonna keep rest of the molecule intact. It's not gonna produce fragments. So that's a milder technique. The other milder technique is electrospray ionization. In this one, instead of fast moving electron bombardment, we just gently spray the electrons, and this is also a gentle technique, electron spray. These gentle techniques are used for biomolecules such as proteins and nucleotides and those, because we want to keep the structure preserved to get more information. So gentle techniques are used for analysis of biomolecules. Any question so far?
No.
Okay, so the remaining uh, chapter will, all the data which we're gonna see in later slides, they all are from EIMS, or electron ionization. Uh, other uh, uh, okay, so those are the other methods like fast atom bombardment, MALDI, or ESI. The principle is same. How the mass is measured is exactly the same. The difference is how the molecular ion is produced. That's the only difference. Some of them are gentle, some of them are more harsher, but rest of the technique is exactly the same. Okay, so all the data you're gonna see later on, it all came from EIMS. So once you started the experiment, you injected your sample, and then sample was vaporized, and then those vapors were bombarded with the electrons. After that bombardment, one of the electron was dislodged, and our sample was transferred into radical cation. Then radical cation accelerates towards the magnetic field. Magnetic field uh, deflects it. Depending on the mass, the deflection will be a lot or very little. So computer calculates from that what is the mass, right? So that's the whole technique. But there's a little bit more to it. There are two important factors after we conduct an experiment. So the first factor is resolution. Resolution means how well a mass spectrometer separates ions of different masses. There are two kinds of spectrometer: low resolution spectrometer, which are found in most common labs. Uh, they are capable of separating ions which differ in nominal mass. That is, that the mass uh, has to be separated by 1 AMU. For example, let's say I have one atom and its formula is C3H8O. I have, can you calculate theoretically what is the molecular weight of this compound?
60.
60, right? And let's say if I have another compound which is C2H4 and O2. Calculate the molecular weight.
60.
60. Well, you are rounding it off, but if you use the exact number from the from the periodic table up to like third or fourth decimal, it will be 60 point something something something. This will also be 60 point something something something. So here 60 and 60 are equal, right?
Mhm.
But we can clearly see, are they same molecule? They are not same molecule. So the low resolution mass spectrometer will not be able to tell that they are different molecule. It's gonna say, oh, the same signal. So both molecules gonna give exactly the same signal at same place, same molecular ion peak. Okay. If I have this molecule C3H6O, its mass is 58, right? Now this one and this one, because now it is different by 2 AMU, right? The difference is 2 AMU. These two will be uh, separated. These two will give different signal for molecular ion in low resolution, but the both red ones will give the same signal. So the point is that low resolution instrument can only differ the ions signal which are at least one or more AMU uh, separated from each other. Okay. So if we have these kind of samples, then we have to use the high resolution mass spectrometer. In high resolution, they can differ as much as 0.0001 or up to fourth decimal place. And if you calculate the molecular mass of these two samples, you will see that after the decimal, they are not same. So in order to separate these signals, we have to use the high resolution. High resolution instruments are mainly used in research and in hi-fi institutions. For most of the experiments, low resolution instrument is good enough. So this was the example I was giving you. Now we can see that after the decimal, the values are different. So high resolution will be capable in to calculate the difference in these two masses. So that's the first important property of any mass spectrometer. The first one is resolution. The second thing is presence of isotopes. Now, all elements which are commonly found in organic compounds, they all of them have isotopes. This table shows most common isotopes and their relative abundance. For example, hydrogen. The other isotope of hydrogen is deuterium. The relative abundance is pretty small. It's not even one. If we have 100 of normal hydrogen, naturally occurring molecule, after 100 molecule, we only have 0.016 molecules of deuterium. Not that much, really small. But on the other hand, carbon, look at carbon. So for every 100 carbon, we have 1.1 of C13. Not that high, but it's enough. One after, it's almost one after every 100. It's not 1%. It's a one after 1.11 after every 100. We'll take a look at the difference. Similarly, nitrogen is this much. The important ones are chlorine. Chlorine is 32.5 after every 100. Okay. So if we get 100 signal from chlorine, normal chlorine 35, the signal from the C37 will be 32.5, like one third, right? Almost one third of the normal signal. Bromine is almost 100 and 100, which is 50-50. So both the signals will be almost same. Okay. Another important thing I would like you to notice here is that most of the isotopes have 1 AMU higher mass than the normal isotope. For example, normal hydrogen is 1, mass of isotope, heavier isotope is 2. Normal carbon is 12, mass of heavier isotope is 13, greater than by 1. There are only 3 isotopes where the mass is greater by 2 mu. One of them is oxygen. So normal oxygen is 16, heavier is 18. The other one is sulfur. So 32 normal, heavier one is 34. Sorry, 4 of them. Then the chlorine, 35 and 37, and bromine, 79 and 81. These are known as M plus 2. And you probably guessed why they are called M plus 2, because their mass is greater by 2 AMU than the molecular ion peak, normal peak. And the other ones are known as, what do you think? What are the other ones are known as? M plus 1, because the isotopes have 1 AMU heavier mass than the normal molecular ion peak. How do we calculate the relative abundance out of 100? Let me show you how do we calculate. For example, in nature, carbon 12 is 98.9% and C13 is 1.1%. So the way to calculate out of every 100 how many C13 is present. So you apply this formula. So you see the percent of isotope multiplied by 100 divided by percent of the normal isotope. I should say percent of heavy isotope. So in case of carbon, percent of heavy isotope was 1.10. So multiplied by 100 divided by 98.90. When you do this calculation, you will, what do we get when we do this? We get 1.11 atoms of C13. So this means 1.11 atoms of C13 after 100 atoms of C12. So the values which you saw in this table, for every 100 this much, for every 100 this much, are calculated by this formula. So these are not the percentages which exist in nature. So this is not 0.016%. That's not what it exists. Okay, so they are calculated by this formula. Okay, so let's solve this problem. So chlorine in nature, so note down these values. Chlorine in nature is 75.77% chlorine 35 and 24.23% chlorine 37. So note down this number. So heavier isotope is 24.23%. and the normal isotope is 75.77%, which is C35. Calculate after every one, for every 100 of C35, how many C37 atoms are present. So you're gonna need to use the same formula which we used here, okay? And calculate the value and then let me know. Okay, so I have answer from Kaylee. Let's hear from others also. So the formula is percentage of the heavier isotope multiplied by 100 divided by the percent of smaller isotope or lighter one. And when you plug in these numbers, yes, anyone?
Yeah, I got 31.98.
Okay.
9798. I rounded it.
Yeah, that is correct.
Okay.
So 31.98% is correct. Okay, so for every 100 of chlorine in nature, see, this means for every 75.77% we have 24.23%. But because in mass spec baseline is 100%, so we like to see for every 100 how much is it. So for every 100, for 100 of C35, we have, well, you can round it off, we can say it's 32 molecules or 32 atoms of C37, Cl37. But anyway, so this is one of one kind of problem you may see in the exam, one kind of math problem.
Professor, in the final exam or exam 3?
Say that again. Oh, this is not in exam 3, by the way.
Okay.
This will not be included in exam 3.
Okay.
Okay, so as I discussed earlier, what's the meaning of M plus 2 and M plus peak? So M plus 1 or M plus 2 peaks are the peaks which M means molecular ion peak. Okay, so for example, this uh, spectrum is of chloroethane. The molecular mass of chloroethane is 64, and we do get a peak at 64. So this peak is the molecular ion peak. So this peak belongs to this molecule or this fragment. Right? Then what is this peak? 66.
Chlorine.
It's not chlorine. It is the same molecule in which chlorine is the heavy chlorine or 37. This is the 35 chlorine. Okay, so this is the same molecule, but the chlorine is replaced by the heavier isotope of chlorine. Remember, for every 100 molecules of normal chlorine, for every 100 molecules of 35 Cl, how many we just calculated? 32 of them are For every 100, 32 will be 37 chlorine. So that's why, so it's almost one third, right? So that's why we get this peak. This peak is known as M plus 2 peak. So M plus 2 peak is obtained when some molecules uh, uh, are obtained from those molecules in which the isotope is replaced by the heavier isotope. So the point is that one third of the chlorine in nature is from heavy isotope and two-thirds are from the normal isotope. That's why if you conduct mass spectroscopy of chloroethane and you have, let's say Avogadro number of molecules injected into it. So for every 132 of them will have this one. And because they contain a heavier isotope, so their mass will also be heavier by 2. So this is a typical pattern of M plus 2 peak. So whenever we have chlorine, we will get additional peak. So we need to know so that this behavior is typical of chlorine behavior. So two peaks will be obtained. So this one will be the normal molecular ion peak, and this one will be the heavier isotope M plus 2 peak. Okay. So the normal peak or molecular ion peak is at 64, which is the molecular mass of chloroethane. And 66 is molecular mass of chloroethane in which chlorine is replaced by heavier chlorine, or 37. Do you see any peak in between these two also? This one.
Mm-hmm.
What do you think? What that peak is?
The chlorine by itself, like a chlorine radical, or?
If it's chlorine radical, that would be 35 or 36,
Oh, yeah.
right? What is, this is 65.
Mm-hmm.
So what that peak is?
Is it the same compound with the 36 chlorine?
36 chlorine does not exist. There are only two isotopes. One is 35, the other one is 37. But you are on a right track, by the way. Yeah, you guessed it right. It is M plus 1 peak. It's one greater than the normal. Where is that extra one coming from? Remember, in molecule, there are other atoms also. It's not only just chlorine. Other atoms can
Hydrogen?
also have heavier isotopes. So this peak is coming when one of the carbon is replaced by C13. That's a C13 replaced molecule. Same chlorine, chlorine with 35, but one of the carbon is replaced by C13. And remember, carbon also have 1% chance, or 1% as compared to 100. So if this is 100, that's why you see this is only 1% compared to 100. So this is M plus 1 peak with C13 replaced instead of C12. See, there are two carbons, right? One of the carbon is replaced by C13. Now hydrogen can also get replaced, but the chances of hydrogen getting replaced is so small that the peak will be so small that we won't be able to see it. And both carbon and both chlorine can also be replaced, but again, when we look at the percentages together, here that one will be here, that's almost it's so small, chances are so small that it won't be visible. So M
Professor?
plus 1 peak is normally observed in case of carbon isotope replacement, and M plus 2 peaks are observed normally whenever we have either chlorine or bromine or sulfur. Okay. Now you may say, ask why we don't see it in oxygen, because look at the percentage. It's only 0.2%. So intensity will be so small, 0.2%, it won't be visible. It needs to have at least about 1% to see. Carbon is 1% and then it's barely visible. So 0.2% oxygen will not be visible. Okay. So this is important. Ratio of M to M plus 2 of 3 and 1. 3 is to 1. See these two peaks. It's almost 3 is to 1 ratio. The big peak and the M plus 2 peak. So this 3 is to 1 peak indicates the presence of chlorine, because chlorine is the only uh, atom whose isotope is the ratio with its isotope is 1 is to 3. Okay. Now these are the molecular ion peaks. One is the normal M peak and this one is M plus 2 peak, right? What can we say about the ratio? Is it 1 is to 3 in this case?
No.
Ratio of these two peaks? The answer is no. The ratios are almost equal. So ratio is 1 is to 1. They both are almost same. And only atom where the ratios are almost same and they are M plus 2. What is this atom? Bromine. Okay. So whenever our sample has bromine, our molecular ion peak will show M and M plus 2 peaks and their intensity will be almost same. Now, if you are confused why here this peak was 100% and this in this here so tiny, because the molecular ion peak may not be the largest peak in all cases. In this case, the molecular ion peak was the largest. That's why it's all the way up to 100. But in this molecule, it's not. So we just compare the intensity with each other, M and M plus 1 or M plus 2. We don't compare this one with the largest. So largest peak in this case is some fragment and 43. We'll learn what those fragments are in few slides later. But for now, remember, the molecular ion peak doesn't need to be or doesn't have to be the largest peak. And in most cases, it will never be the largest key, because molecular ion fragment always breaks down into some other smaller fragments. It's highly unlikely that most of the fragments are molecular ion fragments. So in most of the cases, molecular ion peak is small. This was one of the exceptions where molecular ion peak is so large. Okay. So sulfur is the only other element which also gives a significant M plus 2 peak, because sulfur is 95 and 4%. So relative intensity is about 4%. If, for example, if I ignore this data, just ignore this data. So if I have a molecular peak of 100% here and M plus 2 of 4% here, so this is 100%. This would be a typical behavior of sulfur, because sulfur gives 100 to 4, because we know the ratio between the normal isotope and this one is about 100 to 4. Okay. So for bromine, as we can see, the M and M plus 2 peak. So M and M plus 2 means they differ by mass of 2. So if M is at 90 and M plus 2 is at 92 and they are almost about the same size, what is this typical behavior of which atom?
Bromine.
It's typical behavior of bromine, because bromine is almost same 198. So intensities are almost same for 878 and 8, right? And typical behavior of chlorine is if this molecular ion peak is at, imagine it's at, what is it, 86, and we have, so imagine this is at 86 and this number is at 88. So M plus 2. So this is M and this is M plus 2. So this is a typical behavior of, look at the ratio. Is it 1:3? So big peak, if big peak is 1, sorry, so if the small peak is 1, the big peak is 3 times, right? So that is a typical behavior of chlorine, because chlorine is, if you look at the data, so chlorine is 100 to 33, right? So that's 1 to 3. Any questions so far about the M plus 1 or M plus 2 peaks?
So we'll be given these mass spec charts without the compound, correct?
Yes.
Okay.
We'll go over some sample problems at the end of the chapter. You'll have some idea what kind of problems to expect. Okay, so I would like to go over a formula which may not be in this my PowerPoint, but it will be quite useful to calculate the abundance of M and M plus 1 peak. So remember this formula. So this is called the percentage intensity of M plus 1 peak, or it could be M plus 2 also. So percentage of M plus 1 or M plus 2 peak. It is equals to sum of percent abundance. I'll explain. Let me write the formula first and then I'll explain what's the meaning. Percent abundance of heavier isotope multiplied by number of atoms. You remember this formula. Percent. Okay. Let me explain this formula now. So imagine that I conduct an experiment on pentane. Ignore this one, so ignore these lines for a while. Okay, so just focus on the red lines which I'm going to draw. So let's say I conduct 1, 2, 3, 4, 5 pentanes. This is pentane. Okay. So in pentane, where can I expect my molecular ion peak? And this is the formula of pentane, C5H12. tell me where my molecular ion peak will be.
Around 72.
And yeah, so 72, because molecular ion peak will be same as the molecular mass of it, right? So molecular mass is 72. So my molecular ion peak will be at 72. So this would be 72, right? So my molecular ion peak will appear here, right?
Yeah.
So this is my M peak. A molecular ion peak is called M peak. Now, is there a chance that I may have a M plus 2 peak available here in this sample, in this spectrum? Is there any chance that M plus 2 peak may also appear?
No.
Yes.
If you are saying no, then why no? If you're saying yes, then why yes? Let me hear from yes. Why do you think there will be M plus 2 peak? Just a guess?
Because of the isotope.
Because of the isotope. Yeah, that's the reason. But why M plus 2? Let me hear from the other answer. So someone said no. So why do you think there will be no M plus 2 peak?
Because the isotopes that can form are both C13 and H2. Those are both M plus 1 peaks.
That is absolutely correct. Yes. In this case, M plus 2 peak will not be available or it cannot be formed because the isotopes of both carbon and hydrogen are M plus 1s.
Oh, okay. I see what you're saying now. Oh, I got
Okay,
it.
so M plus 2 peak only
Yeah, because you're going from
forms
12 to
if our
13.
molecule has one of these, either has oxygen, sulfur, chlorine, or bromine. None of these are present in our system. So therefore, there will be M plus 1 peak, right? Now, M plus 1 peak can be from carbon or it can be from hydrogen. Now, the point is, what will be the intensity? What will be the percentage of that? Okay. So that we calculate using this formula. Okay, so let me calculate now. So according to this formula, summation, this means sum of. So sum of all the, so we have two kinds of atoms, carbon atoms and hydrogen atoms. So we need to add both of them. That's the meaning of this. Sigma means sum of all the atoms. So first let's talk about carbon. So carbon, what is the percentage abundance of heavier atom? So let's go back to it. So what is the percentage abundance of heavier atom of carbon? Anyone?
1.11.
1.11%, right? So let's go back, plug in there. So 1.11 multiplied by number of carbon atoms. So how many carbon atoms are there?
5.
5 plus. That's where the summation comes in. Now we will go with hydrogen. So hydrogen, percentage abundance of hydrogen. Go back to the table. What's the percentage abundance of hydrogen? Heavier isotope, by the way. 0.016. So 0.016 multiplied by how many hydrogens?
12.
12. So when we multiply, this will be 5.55 plus, can anyone please multiply 0.0? It's gonna be small number, but just, it's gonna be 0. Anyone with calculator?
192.
0.192 equals 5.7.
Or
Yeah,
2.
let's call. I'm gonna round it off to 5.7 because it's OChem, it doesn't matter. So it means what will be the percentage of M plus 1 peak compared to M peak?
About 6%.
5 point, almost 6%, right? So 6% means if this is 45, let's make it easier on ourselves. Let's make the molecular ion peak to be 60. If the molecular ion peak is a 60, right? So m plus 1 peak will be, how big will it be? 6% of 60. So what is 6% of 60?
10.
10?
No, I don't.
No, 6% of 60 is not, is is 3.5, 3.6, right?
Yeah, 3.6.
3.6. So it's will be m plus 1 peak will be only about 3.6. My scale may not be as accurate, but you got the idea. So m plus 1 peak will appear 1 after. So if m peak is at 72, m plus 1 peak will be at 73, and its height will be 3.6. If m is, the height of m is 60, then the height of this will be 3.6, and that how we calculated it. Okay. Any question about what are m plus 1 peaks and what are m plus 2 peaks, and how the relative intensity of m versus m plus 2 can help us identify whether there is a chlorine, bromine, or oxygen present, or everything okay so far? Okay, so let's continue. So in the beginning of this discussion, we learned that in electron ionization, the energy is about 70 electron volt, which is pretty high, which is almost like 7,000 kilojoules. And energy of most sigma bonds, even the strongest sigma bond, is only about 1,500 kilojoules or somewhere around that. So this 70 electrovolt is enough energy not only to dislodge one or more electron, but it also causes extensive fragmentation. So it breaks down the molecule. These fragments, like I mentioned, they are not stable, but they are stable enough to reach to the detector. As long as they can reach to the detector, we will get a signal, and we do get signal, because you can see we have a bunch of lines, and all those lines means that there is some kind of a fragment, and the mass of, for example, in this case, we are getting one fragment at 29. So whatever that fragment is, its mass is 29. Okay. I can clearly guess because I know what 29 usually is. 29 usually is this fragment. When this fragment, and that's very common, this ethyl, you can count the masses, right? Ethyl is 29, right? So whenever we have a long chain compound and it breaks up, one of the common fragment is ethyl. And ethyl always shows up at 29 because that's the mass of ethyl fragment. Similarly, if you see a fragment at 15, which normally is not there, 15 is rare, what would be the most common guess of 15 fragment? Methyl, right? Methyl is highly uncommon. Uh, okay. So fragments are unstable, and they break up into further smaller fragments. So at the end, we will get a bunch of signals, a bunch of lines. Now, fragmentation of a molecule always produces a radical and a cation. For example, if I have butane, right? And butane was bombarded with electron, fast moving 70 electron volt. And this gonna give me a nice molecular ion, molecular radical cation. Yeah. Any questions so far? This we learned previously. So any questions so far how this happens? Now, this cation is not very stable, and imagine there are more electrons are being bombarded here. 17 electron volts are still being bombarded. So that further bombardment will cause further breakdown. Okay. So further breakdown, maybe one of the sigma bond will now break, one of the sigma bonds. So there we have bunch of sigma bonds here, here, and here. You can break any sigma bond. Which bond you would like to break? It doesn't matter at this point which one you say that it will break. Number one, number two, or number three. I'm just gonna write the
Number
products,
one.
but it doesn't matter whichever you choose. Choose one, two, or three. Which choose either one.
One.
Let's say
Number
number
one.
one. Okay, good choice. So when number one, others can also break. Don't get me wrong. Okay, any bond can break, but some bonds are more likely to break, which we will discuss in next slide. But for now, just let's see what happens. When this bond breaks, this bond is made up of two non-bonding, two electrons, right? When this bond breaks, there are two chances. Either so one of the fragment becomes a free radical, the other fragment becomes a cation. Either this can happen, or this will be cation, then the other one will be free radical. This can happen. Okay. Okay. So in the parent, both radical and cation are on the same molecular ion. But whenever a cleavage takes place, one fragment gets the radical, the other fragment gets the. So two possibilities are there. Now, one of the possibility is more likely than the other, and that depends on the stability of carbocation. In whichever possibility carbocation is more stable, that possibility will be preferred. So now you tell me, is A more likely or B more likely?
B.
B is more likely. Everyone agrees to that? Remember, it depends on the stability of the product carbocation. Whichever gives more stable carbocation, that is more likely. So
Would it
is B more likely? Everyone agrees to that?
Mhm.
Wouldn't it be A?
Oh wait.
And why A?
Because
If you say B, then I would again ask why B, but yeah, let's ask. Let's hear. Why A?
Sorry,
uh,
I was looking at the radical.
No, don't look at the radical. You need to look at the
I
carbocation.
I'm picking A now. Sorry, I agree with A.
So correct answer indeed is A. Yeah, because A, this is primary carbocation and this one is methyl, right? And we know primary is more stable than methyl, so hence A is more likely, or A will be preferred. Does that make sense? Is it getting easier? Slightly, at least.
Yes.
Okay, so that's one concept. Now the others can also break, and then you can figure out that whichever will form carbocation and where the radical will be. Okay. So in this case, A's option is the likely. I'm gonna erase the B option. So whichever fragment, so the way we show it is we break the bond and we show the line going through the bond. Let me fix it. So fragmentation is shown by a line going through the bond. So in this case, I will draw a line So this line shows that there is a fragmentation taking place at this place. The other important thing is, look at my parent ion molecule. Can you tell me, after fragmentation, is the left hand side of the molecule getting a positive charge or the right hand side? So by left hand side means this side, by right hand side means this side. So which side of the molecule is getting the positive charge, left or the right?
Right.
That's important. That's why I'm asking you.
Right.
The right side. So please pay attention. So when you show the fragmentation, whichever side gets the positive charge, we bend that line towards that side. Okay, so we don't pass a vertical line, we bend at the bottom. And the bend is towards the side which gets a positive charge. And that's how we show fragmentation. You can do the fragmentation on other bonds also. Uh, there are certain bonds which are more likely to fragment and certain less likely, that we will discuss in a couple of slides later. And then again, the likelihood of fragmentation depends on the stability of carbocation. You will figure it out by yourself eventually. But for now, this is enough. Any questions so far? Okay. So the fragmentation, likelihood of fragmentation is uh, it dependent on the stability of carbocations. Okay. And remember this order. Methyl is the least stable. So likelihood of a fragmentation in which methyl gets a positive charge is highly unlikely. So that's why I said in previously that a signal at 15 is highly unlikely because methyl never gets formed. Okay. So methyl is least stable and allylic and benzylic is most stable. I hope you guys know what allylic is, but just in case, I'm just gonna. So this is called allyl unit. So it's a propene that's allyl. So whenever we have a cation at allylic position, so this is a cation and allylic position. So this is pretty stable, but this one is primary allyl. Why it's stable? Because it shows resonance. And we know that resonance makes things better. So that's why allyls are stable. So primary allyl is as stable as a secondary carbocation. So they are both same. Although allyl is primary, but because of the resonance, it is same or as stable um, as a normal secondary carbocation. Similarly, if you look at secondary allyl, so secondary allyl carbocation would be, now this is secondary allyl position, right? This is also resonance stabilized. So it's pretty stable. So secondary allyl is almost as stable as tertiary carbocation. And tertiary allylic is the most stable conformation. So what is tertiary allyl? So this one would be a tertiary allyl position. It also shows resonance. So most stable. This one and benzylic. What is benzylic? Anyone knows? So this is most stable.
I'm
This
assuming
is
a benzene ring.
something like that.
Yeah.
No.
Just with one double bond?
Mm, no, none of them. Benzene does not get a positive charge as such. Benzylic is this one is benzylic, but that's primary benzylic. This is tertiary benzylic will be when the positive charge carbon is tertiary here. And you can draw the resonance structures in case of benzylic also. Benzylic has more resonating structures. Uh, so this goes here. It's not CH3, sorry. It's CH2. Right, so this one goes here. You can draw rest of the structures. So you can see that there's extensive resonance in benzylic also. So benzylics are also pretty stable. And remember, benzylic is when a carbon is connected to benzene ring. Just the ring is not benzyl. It's called phenyl, not phenol. The ring alone is called phenyl position. So this is a phenyl substituent. It's not benzyl substituent. Okay, so remember this order. And the reason why are we remembering this order is that this will predict us, or this will help us predicting in the fragmentation pattern. So fragmentation will take place at those positions which gives us preferably the allylic or tertiary or benzylic. If that's a possibility, those will be places where fragmentation will happen, and those will be the places where a positive charge will be present. And those fragments will be most commonly detected whenever we conduct mass spectroscopy of any molecule. Any questions so far? So all the information needed and all the theory behind the technique and what the technique is, so that's all done. The remaining is how to interpret the data and problem solving. So any question about the theory part of the mass spectroscopy? What is a mass spectroscopy? How we measure it? What's the meaning of fragmentation? Why fragmentation takes place? What is a molecular ion peak? What is M+1 peak? What is M+2 peak? And why do they appear? What is the meaning of relative intensity of molecular ion peak and M+1 and M+2? Why in some cases M and M+2 are almost same size, and in why in some cases they are not? So any question related to that, I'll be happy to answer. Everything okay so far? Okay, so let's take a small break, and the remaining chapter focuses on interpretation of data. So we will uh, go over that after about 10 minutes break. Would that be okay? Man, you guys are quiet.
Sorry, yes, that'll be. I thought I was talking, but my mic was off.
Okay.